Hello everyone, welcome to video lecture series on microcontrollers and applications. We are at lecture number 10. In this lecture, we are going to discuss unconditional control transfer instructions of 8051 microcontroller. In last class, we discussed conditional control transfer instructions, where we discussed introduction to control transfer instructions, syntax of control transfer instructions, working of control transfer instructions, and examples of control transfer instructions. In this lecture, you may achieve three learning outcomes. They are identify and use unconditional control transfer instructions for jump and subroutine calls, difference between types of jumps, sjump, ajump, ljump based on their address range, write programs using calls, acall, lcall, and return to manage the modular code. These are the unconditional control transfer instructions supported by 8051 microcontroller. They are SJMP, AJMP, LJMP. So here SJMP stands for short jump, AJMP stands for absolute jump, LJMP stands for long jump. Here all these three are jump instructions, but the destination range is different. How the destination range is different, we will discuss one by one in the next slides. But you can see here the difference between number of bytes occupied in the memory and number of machine cycles required to complete the instruction and opcode of corresponding instruction. So this may you can get from the data sheet of the 8051 microcontroller. So you can see here SJMP requires only 2 bytes and 2 clock cycles to complete the execution of this instruction. AJMP is also same 2 and 2, but whereas LJMP requires 3 bytes to store this instruction in a memory, but it is also executed within 2 machine cycles. Similarly, we are having JMP at the rate A plus DPTR. So this requires only 1 byte in memory, but for execution it takes 2 clock cycles. Similarly, A call, absolute call is also 2 bytes are required, 2 machine cycles are required to complete this instruction. Similarly, lcall is a 3-byte instruction to store in a memory, and it requires 2 machine cycles to execute this instruction. Return only 1 byte, return I is also 1 byte. For execution, it both takes 2 machine cycles. And these are the opcodes you can see within the uh, data sheet of 8051 microcontroller. Then coming to SJMP. SJMP means short jump. As in previous slide, we know that it is a 2-byte instruction. It is having 2 bytes. This is 1 byte. This is another byte. The first byte represents its opcode, and the second byte represents the relative address. Relative address. It is a signed 8-bit number. Signed 8-bit number. Relative address is nothing but a signed 8-bit number. The syntax is SJump relative address. This instruction unconditionally jumps to destination address specified relatively in the instruction. So that means here relative referred to 8-bit relative address, hence the target address is minus 128 bytes to plus 127 bytes relative to PC value. Here you can see here sjump here. So this is the example. You can see here. Let us consider This is the instruction, sjump instruction. Here this is the label or relative address. Actual relative address, how the 8051 computes, we will see now. How FE is placed. Let us consider this instruction is availability location of 0700H. Sjump is available and 80H is the first byte, okay, opcode. And this FE will be stored in next location. So that means this instruction occupies two locations in memory. These are the two locations is occupied by this SJMP XX instruction. And then while executing this instruction, the PC will have 0702. Why? Because PC is always points to the address of the next instruction. So that means the PC will have 0702H. But where we are specified this relative address to the same instruction. So to generate the same physical address, here we are placed -2. -2 means 7002 plus -2 means the actual physical address will is equal to 7002 minus PC value plus the address relatively specified within the instruction. What is the address specified relatively here? -2. So that means 7002 plus -2 is equal to actual physical address is equal to 7000 only. That means again this instruction forcibly places this value with 0700. So that means this instruction is infinitely executing. Okay, continuously this instruction is executing. This is the operation of sjump instruction in 8051 microcontroller. Instruction is the jump instruction. Jump stands for absolute jump. This absolute jump uses 11-bit address. It is a 2-byte instruction. This is first byte. This is a second byte. Okay. In the second byte, A0 to A7. These represent the 8-bit address, and the A8 to A9, A8 to A10 are also 3-bit address. Total, it is a 11-bit address. It is a 11-bit address. Remaining 5 bits are provided for its opcode, its operational code. The AJMP instruction transfers program execution to the specified address. The address is formed by combining 5 higher order bits of the address of the following instruction from A15 to A11. The 3 higher order bits of the opcode, 3 higher order bits of the opcode, A10 to A8, and the second byte of the instruction A7 to A10. The destination address must be located in the same 2 KB block of program memory as opcode following the instruction. After execution of this instruction, no flags are affected. And here, the example for this one is, let us see now. Here, this is the opcode, okay, opcode and AJump label. So this AJump is available at location 40H, and let us consider the first byte is opcode, and the address is 00. So here this is AJump, and while executing this instruction, the PC is having 0002. PC is having 002. Then here actually as per the operation, five higher order bits of the following instruction A15 to A11. A15 to A11 is copied as it is for this instruction, but whereas remaining 11 bits are taken from here and here, whatever the address is specified here. So that means here we are specified 0200H. Okay. So in this 5 bits are nothing but 0000 and another 0. These are picking from higher order bits of the next instruction only. And 0100. This is 2. So from here onwards, 1000 onwards, we are picking from the destination specified within the instruction. Okay. Then, so whenever this instruction is executed, it takes this 5 bits from the next instruction, remaining 11 bits from the uh, specified address in the destination, and then it will goes to 0200 location, where in this location a move instruction is available here. So that means how it is computing the uh, actual physical address, 5 bits from the immediate instruction and 11 bits from the address specified within the instruction. So in this way, it will compute destination address for absolute jump in 8051 microcontroller. So then long jump, L jump. L jump 16-bit address. It is a 3-byte instruction. In this case, the first byte is completely opcode. Second byte is higher byte of the destination address. Lower byte of the destination address is third byte. First byte is opcode. Second byte is higher byte of the destination address. Third byte is the lower byte of the address. So this instruction unconditionally jumps to destination address specified within the instruction. The encoding is very simple here. You can see this first byte is opcode, remaining two are the destination address. So let us consider how it will be stored in this memory. You can see first let us consider this is available at a location 00F008H. As per this, the opcode is 02 and L jump delay. So, but here it will specify higher order first in next location and the lower order is next. So it is a completely 3-byte instruction. When this instruction is executed, it will loads this value to PC directly. That means it will execute the instructions from this address. While executing the this ljump instruction, the PC will have F triple double zero BH. But once this execution is completed, the instruction forcibly places PC with 2000. That means your controller will execute the instructions from 2000H onwards. This is the operation of unconditional branch instruction, ljump instruction in 8051 microcontroller. Next one is jump at the rate A plus DPTR. This is also similar to ljump instruction, except here the 16-bit address is indirectly specified with the help of DPTR and A register. That's it. So the opcode is only 73H and the corresponding addresses should be, we need to load before execution of this instruction. Before execution of this instruction, DPTR should have a 16-bit number and A should have a 8-bit number. This instruction jumps unconditional to a address specified by sum of dptr and the value of accumulator. Then let us consider first we need to load dptr with some 16-bit number. 2000 is loaded. A is loaded with the 10H. Then when you execute this instruction, and one more important thing, it occupies only 1 byte in the memory location. So that means this is the address of the this instruction, and this is the opcode. And while executing this instruction, PC will have only 09 only. And whenever this instruction is executed, so it will add 2000 plus 10. So 2010H location. So that means once this instruction is executed, PC is forcefully places with 2010. That means it will execute the instruction from 2010H location onwards. Next, we need to discuss call instruction. Call means call a procedure. Procedure is nothing but a subroutine. Then let us see now. I am executing a mainline program like this. PC is having 0100. My program is starts here. Let us consider one instruction is available in this location, another instruction is available. Like I am executing like this, then I need to call a procedure now. Whenever I require a procedure, I need to call a procedure with the help of a call instruction. Whenever a call instruction is executed, first the stock pointer is actually incremented by 2. Okay. While executing call instruction, actually, the PC is having this value. Okay. And one more important thing, when you are going from mainline to subprogram, let us consider a procedure. This is mainline program. When you are moving from mainline program to a subroutine program, first the PC value should be saved onto the stack. Why? Because after completion of this procedure, we need to return back where you stopped. That means the return address must be. Return address is nothing but while executing the call instruction, whatever the content is available in PC is called as return address. The return address must be saved onto the stack. So that means whenever a call instruction is executed, the stock pointer is incremented by 2. 07 means it is incremented by 2 means it creates two empty locations 08H and 09H. The PC lower value will be stored here, PC higher value will be stored here. That means PC lower value is nothing but 07. Here 07 will be stored, here 01 will be stored while moving, and then the PC is loaded with whatever the destination address is available here, PC. Once PC gets new address, that means 0200, it will jump to a procedure. So this procedure will be executing now. So in the procedure, some instructions are executed, and at the end of each procedure, there must be a return instruction. Why? Because already we saved the return address, whatever the return address, this is called as a return address. Return address is already available in stock. We need to retrieve the stock. So once return instruction is executed, the return address is placed in PC again. Okay. Once PC gets this address, it will be executing the instructions from this location onwards. At the same time, while returning, the stock pointer is decremented by 2. That means it will have 07 only. Once you are moving on to subroutine program and return back to the subroutine program, the stock pointer value is as it is. So this is about a call instruction. So let us see how this A call will work in 8051 once again. Okay. The call instruction is used to transfer execution control to a procedure or subroutine. Call instruction is used to transfer execution control to call instruction is used to transfer execution control to a procedure or a subroutine. Okay. Then types of calls A call and L call. The operation of A call and L call is similar except here which uses a 1-bit address similar to A jump instruction. It uses 16-bit address. Remaining operation is similar. So let us see the operation. So first, whenever lcall instruction is executed, the stack pointer is incremented by 2 and the PC value pushed onto the stack. PC value will be pushed onto the stack. These are the operations are performed whenever A call or L call instruction is executed. The only difference is here it is uses 11-bit address, it uses 16-bit address. Loads PC with address of the first instruction in the procedure. Okay, and then loads PC with address of the first instruction. What is the address of the first instruction here? This is the address of the first instruction. So within the procedure. And from while returning from the procedure, the return instruction must be there, which is used to pop higher order and lower order bytes from the stack. Okay, that means to retrieve the PC value onto the from the stack. So return instruction is used, and the return instruction is also decrement the stack pointer by 2 and decrement the stack pointer by 2. This is the operation of A call instruction and L call instruction. Next, A call. A call stands for absolute call. The call instruction calls a subroutine located at the specified address, but within the 2 kilobytes of the same memory space. And it is a 2-byte instruction, you can see, similar to A jump instruction. And here it is this is the encoding for the instruction. Already you know how to compute the destination address. In this case, the subroutine that is called located within 2 kilobyte program memory as the opcode following the A call instruction. Compulsory, we need to call a subroutine. That subroutine must be within the 2 kilobytes where the call instruction is called. And the example is A call. The next instruction is L call. L call stands for long call. The long call instruction calls a subroutine location at the specified address. It is a 3-byte instruction, and the encoding is the first byte is represent the opcode, remaining 2 bytes represent the address of the destination, but the second byte represent the higher order address, the third byte represent the lower order address of the destination. The address of this subroutine is represented with A0 to A15 in the instruction. The instruction calls a subroutine anywhere in the program memory. The example is L call delay, then return an I. This instruction is used to return from the interrupt. Return from the interrupt. Return I instruction is used to end an interrupt service routine. The instruction pops higher order and lower order bytes from PC, just like return instruction. In addition, and also it decrement the stack pointer by 2. In addition, restores interrupt logic to accept additional interrupts. As compared to return instruction, this instruction also performs retrieve the PC value and decrement the stack pointer by 2, but it also restore the interrupt logic. So when in 8051 microcontroller, actually whenever an interrupt comes, it will disable remaining interrupts. So that means to enable further interrupts, so it has to restore the interrupt logic additionally. So that is an additional operation of return instruction in 8051 microcontroller. Next one is the NOP instruction. NOP means no operation. In 8051 microcontroller, every instruction is performing one specific task. And but this is the only instruction which does not have any operation, but it is having a significance. What is the significance? We will see now. NOP means this does nothing. This instruction does nothing. None of the operation will be performed. But execution continues with the next instruction. That means let us consider here if NOP instruction is there, it won't perform any instruction, but it will pass the execution control to next instruction. And no registers or flags are affected by this instruction. Whenever there is no operation, no registers, no flags will be affected. And NOP is typically used to generate a delay in execution or reserve space in a code memory. So let us see what is how it will generate the delay in a program. Suppose, for example, I need to repeat. Uh, suppose, for example, I need to let us consider NOP reserves 1 byte in memory and 1 clock cycle to complete its execution. It does not think, but it consumes one memory location, and it consumes 1 clock cycle, one machine cycle for execution. Because of these two, it is having two applications. One is this will be used for reserve space in a code memory while hand coding. While hand coding, we can reserve a memory location by placing NOP instruction while we are using hand coding. The another application is it consumes one machine cycle. Suppose, for example, I need to generate a delay of 10 seconds, 10 milliseconds, or 10 microseconds. Let us consider 10 microseconds. Now, I'll repeat this NOP instruction. It will take one machine cycle to complete. I know. So, if I execute 10 times the same instruction, it will consume 10 machine cycles. 10 machine cycles into 1 microsecond gives the a delay of 10 microseconds. So that means we can increase the delay of a loop by repeating this NOP instructions a number of times. These are the applications of NOP instruction. And summary, in this session, we discussed the following key points: syntax of unconditional control transfer instructions, working of unconditional control transfer instructions, examples of unconditional control transfer instructions. Next class, we will writing the basic assembly programs for 8051 microcontroller, combining data movement, arithmetic, logic, and control flow instructions. These are the sample uh, questions you may solve yourself. And today, code is in embedded systems. Unconditional control instructions are like trusted shortcuts guiding the program where it must go without asking why. Thank you.